So I guess Daniel from Tel Aviv will tell us about how to observe Floquet topological order by symmetry resolution.
Okay, so thanks for the organizers for inviting me, the ASQC5 committee, and for organizing this event. So my name is Daniel Azses, and I'm a PhD student at Tel Aviv University under the supervision of Professor Azses. And I'll talk about the recent work that we have, which is related also to this algebraic structures like homology and the examples that we saw previously. And let's start with some long introduction about the theory and some past results. About theory. So mainly I will talk about how the topology, the symmetry, and the Floquet components combine and affect the entanglement of the states or structures. So first, let me say the usual definitions about the topology. So a trivial topological order in condensed matter when we take an Hamiltonian and we vary it with the parameter alpha. So, okay. So here you see the H alpha that changes. You have some energy spectrum, and if this energy spectrum stays gap along this variation, then we say that these two Hamiltonian are connected. So basically, they should be local, of course. And if we do a transition, we don't close the gap in the same phase, in topological phase. But if not, then we have phase transition. And what happens when we have a phase transition is that we have maybe non-trivial topological order. So we will focus only on ground states that have basically a connection to a product states according to this definition. And a simple definition without this condensed matter setup is to look about finite circuits, about finite depth quantum circuits. So if you can take a product state and apply a finite depth quantum circuit and construct another ground state of local gap Hamiltonian, then we can say that these two are in the same phase. So the proof of going from here to here is not very difficult, but it is mostly technical. So basically taking this variation of e to the minus I integral over H alpha varies from 0 to 1, and seeing how actually this happens in a circuit form. So you need to vary the Hamiltonian and do many evolutions. This will be finite because alpha here varies on a finite scale always. You can scale basically. And this is all that I talk about topological order because we don't want it in this talk. We want to have short-range entanglement. So basically no topological order. So all the states will be connected to product states. And what we have after this trivial topological order. So the first problem is that in 1D, all the spin chains are actually trivial topological order. This is related to the MPS and S construction. So in this case, we can add a symmetry. So in 1D, if we add a symmetry, we can actually see that if we do a variation, very similar to the previous definition, with symmetric finite depth circuits, and not just any circuit, then we can divide a class of, for example, trivial topological order into subclasses of symmetry protected topological phases. So the definition is also a little bit technical. So if you can generate it by a finite supplementary, you have actually trivial topological order, and then you say that there are equivalence classes under symmetric finite depth. So you see here in the figure that you have all this blue bubble of many possible ground states of local gap Hamiltonians. Yes, and some of them will be connected with symmetric depth circuits, and some of them will require you to use some non-symmetric finite depth circuit, and that's why they will not be in the same phase. basically, if you can take a state and move it, transform it to another state with a finite depth circuit, then they're in this same more beige color bubble. And of course, all the states here are symmetric. Okay. So now we will combine this definition of topology and symmetry, and I mostly here outline some known results about how they affect also the entanglements. So the first thing is that we want to cover our settings. So we have 1D symmetric protected topological phases. So all this stuff is again in 1D. And we have a spin chain. It has some sides and it has right edge and left edge. And basically, the symmetry will always be on-side symmetry. So the symmetry acts the same on every side. They act the same on this side and every side. And it will have some finite structure. Like Z2 times Z2 is the most famous one. And it has like identity, D1, D2, and their multiplication. And on the ground state, we basically have trivial if on the edge the symmetry have commutation. So basically, this is related to previous stuff that talked about the projected representation of the edge. So the symmetry can act on the edge differently from how it acts on the bar, as we saw, for example, in the first talk. And what happens if it is trivial? It just you don't get this projective factor. But if it's not trivial, then you get some phase. Yes, and this what happens and why we get edge modes. Now, this can be much more formalized with the MPS formalism. I'm not going into the MPS formalism for this, but this is the simple example. Now, this is why we need also Z2 times Z2. So if we take just Z2, then we get a problem. So with Z2, we get that we have an identity. The identity cannot get you a phase, basically, because it always commutes in the projected representation also. So you don't get the phase that you want, so you don't have a ST. So this is why we need to start with Z2 times Z2. But we will see also in this talk that Floquet actually saves you. So if you have Floquet drive, then it can actually add you another structure to the symmetry, the time constellations, and this will add you the SPT phases in the Floquet settings. Now, let me go to how we recognize SPT phases. So we have this framework of what is called symmetry resolved entanglements. So we take the reduced density matrix. So basically, you take the ground state on this chain, and you cut it in half, and then you trace the B subsystem, yes, that you cut out, and you get a block. Now, because the symmetry is on site, it induces a block structure on the reduced density matrix. So in this block structure, you will have blocks that have the eigenstate with some defined symmetry. So for example, if we have a parity symmetry, so you can think about 0, 0, 0, 1, 1, 1 states as having a +1 parity, the number of ones is given. So in this block, you will have only even such states in this block, and here you will have those with odd. But you will not have combination of even and odd, because you trace the B subsystem, and the symmetry also got traced there, and you have the subsystem symmetry in these blocks. Yes. So this is the nice thing about the on-site symmetry, and we can recognize SPT states by having their block similar or degenerate in some way. So in a trivial state, what you usually have is non-equal blocks. So you have some blocks here and some other block here. So the state is symmetric. So you still have blocks, but you will not have interesting block structure. If you go to the SPT phase, you will see that the blocks will be actually the same for this is, for example, for some certain symmetries. So we see here for more different symmetries. So for Z2 times Z2 and Z3 times Z3, you see that if I take a trivial state, I get something like that. So in the x-axis, you can see the sectors. So we just enumerate them, 0, 0, 0, 1, and so on. And on the y-axis, you actually see the eigenvalues of the reduced density matrix that's related to these blocks. So each block gives you its own eigenvalues. And what we see here is that the topological, so there are many topological phases, but you will see that they are all degenerates in their way for this example. Now, so how do we compute this? So I go over the computation to show you actually how you some sort of derive these results from a very nice framework of Chantal. So let me start with projection of the bit. So all the talk is about, again, about finite abelian symmetry groups. I not talk about non-abelian or more complicated groups, and basically because of this projection. So what's nice about this finite size abelian group is that you have a very simple representation with unitary matrices, and you can actually talk about characters. So a character is just what's called 1D4, and basically takes the, so in the first talk we introduced already the characters. They take an element of the group into the complex plane, actually the S1 sphere. So they have modulo 1, just a phase, and they have this nice relation. It's basically what's called 1D homomorphism sometimes. And for the projections, if you try to think about it, you can write them as follows. So if you want to project into the sector Q, you can enumerate. So there are only a Q number of characters exactly with the size of the group G, because it is finite abelian and so on. And you can write the projection in this nice form. So this is just, for example, let's talk about Z2 symmetry. So we have one matrix U as identity and one matrix U, let's say X. Yes, you can always take and do a notation to it. And you will have a characters of 1, 1 and 1 minus 1. Yes, and the projectors will be or I plus X or I minus X. So you can see if you apply X on I plus X, it goes to I plus X. Yes, this is a very nice projection. And if you apply I minus X, you see that you get a minus 1 sign, because X squared will go to minus sign. So this is why this is very, very useful. And the SRE calculation now proceeds basically by projecting the reduced density matrix. So we want to talk about, for example, an entanglement. We cannot measure the eigenvalues, yes, of each block. This is very hard to measure eigenvalues of some operators and quantum computers and so on, but we can measure with some tools this quantity, for example, trace of 1 to the power of n with n copies or randomized benchmarks, and there are some ways to do this. So we want to measure this, but we want to project
in this case, if you have any copies, then is natural, like is it?
Yes, yes. So n is in 1, 2, 3, 4,
okay,
etc.
Yes.
So 1 is not interesting because trace of 4a is 1, but it is interesting in this case. So if you try to look at the blocks, so the blocks may have different trace.
Yeah.
So in this case, we talk about the Rényi symmetry resolved entanglement, which is the Rényi entanglement projected to some sort of charge.
But you are not considering like n equals square root of 2 or something.
No. Okay. Only integers. Okay. So there are of course some books that talks about how you take n to 1 and take derivatives and you recover the von Neumann entanglement and this, but we cannot get it with a quantum computer, sadly, because we can only do non-negative numbers of copies. So we can do 1 or 2 or 3. There is also a method to measure this with randomized measurements. So you somehow take your state and you apply random measurements on it, and you can somehow get some observables from it. So it's a very nice way, but the copy way works more famous, and it was used a lot to measure these things. And now what we will focus about is, because you see this Sn of charge Q basically transforms to some linear combination of some object which is trace of U applied on the subsystem A with this symmetry G, or A to the power of n. So this is the projection to the Q sector in the reduced density matrix. So you need to apply the symmetry only on the reduced subsystem. And actually we get some sort, so you can think about it as a group Fourier transform actually of the SNQs. This is like a different approach or way to look at this. Now, if we want constant symmetry of the element, basically that all the sectors are degenerate, yes, as we saw, for example, in all the cases of the topological in the previous slides. So we want ZG to be some sort of a delta function. So only the I will contribute something, yes? And then when you take the linear combination, so all the others, for example, where UA of G is not identity, they will be 0. So you will see that Sn of Q will be fully degenerate if this is the case. So let's see how we explain this. So I use the cosine definition. So it was introduced already, but I'll go about it quickly. So you have a projective representation, PA times PB is not PAB, but you have a cocycle factors, and they have this condition because of associativity. So if you do associativity of this projective representation, you get this. And they also have what is called covariant transformation. You can apply a phase to each of these P, and this is leads to the same cocycle factor systems, and this is being equivalent for the representation. And what is omega of AB? Sometimes it's called the group cohomology, and it actually classifies these different cocycles. And what we can actually think about these cocycles, we can think about it in a graphic form. So this is a very nice form that Chen et al. Introduced. I think it was a testimony, but they show it very nicely. So you can take this omega of A and B and transform it to another mu. So they are called cochains, not cocycles, and then the mu of 1A and AB. Now you can check from all this definition that if you apply a G over this mu, it stays the same. And this actually leads to taking and seeing the cocycle condition is acting on this, for example, tetrahedron. So you have a closed surface, and each of these mu's will give always 1 on a closed surface. So if you multiply all of them, and you have also arrows to say which is the first and which is the second one, you have this expression. So basically, we have this condition at nu A of B. This is like the symmetry of the states, so states are symmetric. So we get this condition. This is just say that only the topology matters. So here you see that we actually can add points and remove points, and we always use this in some way. And so you can play with the geometry very nicely. And that leads to defining state. So this is the ansatz of Chen et al. In their paper. So they take some sort of surface with the points inside, which they call G star. So they take a DSPT state and they write it using D+1 and some sort of this graphical model. So they add a dimension, which is a G star here, and the qubits or the usual degrees of freedom lie in this 1D circle. So this is, of course, in 1D, but their construction is very, very, very general. And what they say is that if you want to say what is the state, so each phase, so you choose, this is each point here is from the symmetry group. So for example, for Z2, you will have a qubit, 0 or 1. But for Z3, you will have something more complicated. And the phase of each element here, of choosing this GIs is actually just a multiplication of this mu after you, so you can fix this G star to be something exact, you can fix 0, or you can sum over it also. Yes, so this is actually the same as they claim. And this way we can actually construct for each aesthetic phase some sort of state which is a fixed point. They call this also a fixed point, and this actually helps us to compute things, because on this model it is easier to compute the ZGs that I expect. So you can play with these models and you can say that the trace is 1 because this is a closed surface. So you see this is like the graphical definition. You can talk about the reduced density matrix, just tracing, but not over all the cubes. So I don't trace over the A system. So here I have 3 in A, but I didn't trace because I have here, this is one state, this is the other state. Is we can do add the UAG, it's like acts on this, and it adds a factor of G to the state. Yes, so how the symmetry acts in this basis, just multiplying each point with G. So basically, if it will act over all these points, so because the mu has this symmetry condition, it will stay the same, but if you act only on this A subsystem, then you get something different. And then you can actually talk about how rho is affected by this, and you add all these things, and you can actually calculate these things. So I think that for the interest of time, I will not talk about all this calculation, but I just tell you that by moving all these triangles around and playing with the definitions, you can actually get a factor which looks like this. So if you sum over something and you do some sort of a twist to the symmetry and another variable that you sum over it, this will tell you if the ZG is 0 or not. And most of the time it will be 0. And for maximally mixed, for some sort of cocycles, it will actually almost always will be 0. It will give you this constant ZG. Let me skip, but here is a nice numerical, or you can actually get it from computation. So if you say that you want to look on Zn times Zn, so you know that the cohomology of this is given as Zn, these are known results, and you can actually go over all these SPT phases. So Z2 times Z2 here, you have the cluster states, because m equals 1 is the non-trivial SPT. And you can see that you have all the sectors the same. So here I write the signature, basically how many blocks have the same trace. So how many blocks are the same. So here you see that you get completely degenerate sectors, as we saw in the figure before. And also this happened for Z3 times Z3, but for Z4 times Z4, you see that you have very interesting thing happens. And you actually can say that this actually depends on the GCD of N and M. And this entanglement structures somehow change. But we can actually say more about how this degeneracy changes. And we can talk about how this perfect equidecomposition is actually equivalent to having maximally non-commutative cocycles. So if you play with this proof and do many things, there is something that is called G0 in cohomology, and this is how much the cocycles are commutative. So maximally non-commutative cocycles basically means that they are non-commutative at all. So G0 is just having the one element, the identity element here. So only this one in G and this interesting commutation. And basically this will also mean that GZ, which equals to G0, this is what we proved in the paper, and will also be 1. And because this is like Fourier decomposition, it means that all the sectors are degenerate. So you see that if you have maximally non-commutative cocycles, basically say the same as having perfect equal decomposition. And I also add here that maximally non-commutative cocycles were very much connected to having MVQC. So you don't really need all of them, I think, to have this non-commutativity. It's also if you have a subgroup of the symmetry with this non-commutativity, like if you happen to find Z2 times Z2 that has this non-commutativity, I think you still can do a MBQC with this. And this must be related to this with the composition because they are very related here. So this is all that I wanted to say about the topology and symmetry. And now I'm going to the Floquet settings. So in the Floquet settings, we have basically a Floquet model. So why we want to actually talk about this Floquet settings? Basically, because you saw that for Z2 times Z2, you need, so for 1D SPTs, you need Z2 times Z2 symmetry. But sometimes you want to go very easy and ask if you can do things with only Z2 symmetry. And the Floquet settings actually allows us to do this. So the Floquet model is where you have an Hamiltonian, which is time periodic with some period T. And the easiest example is just some Hamiltonian that changes between two Hamiltonians. So you apply for like 1 second one Hamiltonian, for the second for other Hamiltonian, and then do it. So it will have some sort of periodicity. So we will have two Hamiltonians. One is known as the paramagnets with some coefficient, we don't really care. The second will be just which is usually Ising model, it's the interaction. And we model it as a circuit like that. So you apply one layer of some sort of Rx rotations, which is e to the minus I with some angle alpha, and then you apply this ZZ couplings. Now we have a symmetry of this model. So this e to the minus IH1 times e to the minus H2. This is known as the Floquet operator, and it has a symmetry. So this symmetry is a Z2 symmetry. You can see that if you have all the excess here, easily you see this commutes with H1. With H2, you also see this because each Z anti-commutes with the excess. So two of them will commute. And people already figured out this model. So in the fermionic settings, I would say, so they did the transformation to the Majoranas, and so you can transform this model to fermionic models. And they figured out that here you have a topological part. So they say that this Floquet part of this phase is topological, and all the other are either symmetry breaking or trivial, so it depends. And what we want to show is that this topological phase has different properties, and how these different properties actually connected to the entanglement is what we want to show here. So we will actually add now the topology and the symmetry to this Floquet settings. So first I need to go over some definition. What is Floquet SPT in the physical mobile settings? And so there is no Hamiltonian here. There is only the Floquet operator. So basically, almost everything that we said about Hamiltonians, just you turn it and you talk about the Floquet operator. So if the Floquet operator has symmetry, and this is good. So it has a Z2 symmetry. And now there is some sort of theorem that you can always decompose this Floquet operator into something of a phase in the bulk. So this e to the minus I f is a phase in the bulk. And you have two edge operators, FR and FL. And these operators will have some sort of projective representation with the symmetry. So how does it work? So it is trivial if FR simply commutes with GR, for example, and it is an SPT if you have a phase here. So this is the difference. This is how they define it. And this is very related to the charge pumping that was discussed in the first talk, because this phase will somehow change the charge, you see, because the symmetry now have another phase. And again, you have here topological invariance. So how this all combined with the entanglement after you see this. So what actually happens because of this usual non-commutativity over GF? What is if you happen to cut the system here? So let's cut it at the middle. then the symmetry here acts differently. As FR and FN acts here and here, and it will causes a charge to pump in this direction, and it will change the symmetry sectors of this part. Basically, you will get some sort of a difference. So let's see. So I have here the usual definition of this symmetry resolved entanglement. This is what we usually have for a trivial state. But what happens when I apply the Floquet operator? So after applying the Floquet operator, if you do the algebra and FR has this SPT commutation relations, so it adds a phase there. So this phase will change the sectors. Yes. So what happens is that if I choose symmetric eigenstate e to the minus if, so I don't want this phase in the back. Yes. And then I have, so you remember you have projection to the symmetry like I plus x. So now if I have this f acts on I plus x, so it will commute with I. But if it is an SPT with this x symmetry operator, it will add a -1 phase. So from I plus x, I go to I minus x. This is the different sector. So basically what happens is that, so for the trivial nothing will happen, of course, because it simply commute. But for the FSPT, we'll have simply some sort of we call it sort of a zigzag. So after each application of F, you go from the entanglement of the even, goes to the odd, goes back to the even, goes back to the odd. So you get very, very, very rapid oscillations. And these oscillations are what we want to see in the experiments. So let's see the experiment. So what we have here is some very complicated protocol to create this symmetric state of the e to the minus if. So it is very, very hard to just find this e to the minus if. It is some sort of functional of all the, it's called quasi momentum, I think, or something. And because it is so hard to find, we will use the adiabatic theorem. So we start from very easy point, and then we adiabatically change this point, and with this way we will not actually damage this symmetry of e to the minus if. So this is the idea. We do adiabatic sweeping along the path, so we choose this path or this. Slowly. And here we will have a phase transition. So you remember this very nice. So we have this very nice zigzag here, but when we go over the phase transition, there is no longer any zigzag. So you will see that basically from rapid oscillation you go into something else, and at each point you apply the Floquet operator with a little bit of deviation. And we hear some, so this is, let's say this is some sort of ansatz that we will always remain in this symmetric eigenstate e to the minus if. So this is not exactly the adiabatic theorem, because the adiabatic theorem talks about Hamiltonian, so if you change Hamiltonian closely, you are still an eigenstate. But here you will change f slowly, and here it is not clear it is an eigenstate. So is there a question?
Yeah, there's a question here. I mean, one law that your system is a little bit different. There's not really Hamiltonian, that you want to leave the ground state off. But I mean, when I see a adiabatic path across a phase transition, doesn't sound so good, because I mean, in the conventional setting, you would have the gap closing, and then it would be very, very hard to be adiabatic. I mean, your adiabaticity makes maybe 5-step. In a real world setting, I don't know. And that you can't go across a shrinking gap in that way. So I wonder, does this type of argument simply doesn't apply, or is there a counterpart in your Floquet theory setting? If there was, what do you do with it?
So this is so it's correct that with Hamiltonians you have a gap, and then if you go even very slowly along the phase transition, it will be problematic. But in these Floquet settings, actually here, what says that this part is topological are two modes. So you have the zero modes and you have the pi modes. There are two eigenvalues of f, like yes, it's like the 1 minus 1, yes, and what happens there is actually that one of the modes gets shifted from pi. So it's not exactly like a gap. So there is no. It's hard to get the notion of gap for the Floquet operator because it is generally like continuous thing. Yes, and they indeed go and cross many times. Many levels will cross here. So there are works about some chaos in Floquet, non chaos. But these settings work because we actually just focus on this pi mode. So with this pi mode goes on pi, then we start to not see this rapid oscillation. Yes. So the initial state is actually a combination of two states exactly of this Floquet operator. So they will never almost touch in these settings, but they do have. There are many. There is a leakage from the pi state here to other states because it starts to go near the states near it. But if you have, for example, very so N is very large system, but also you go very slowly. So it's always related. So you need to go slow enough. So I think it was L to the power of R or something, or maybe squared. But if you go slow enough, then this gap is enough to keep you, actually protect you from this leakage. But yes, you always need to choose. So infinite system, it is not important, it's not possible. But we have too many levels, and you will actually lose.
Okay, no, that's okay. It's a finite system, and so you just need to be slow enough.
Yes. So we take finite system, we are just slower than the system. Then, so why it is easy to actually simulate this? So it seems to have, so we will get a system length like n equals to 100 spins, 50 spins. It is really hard, but here because we can map this problem to three fermions with dot and Wigner, and this is why the topological phase was so clear and all of this. You can actually do it in polynomial time. So I'm not explaining too much the details, but you can read about it later. So now here are some numerical simulation. So there is even an odd, but you cannot see them because of the rapid oscillation. It's so rapid, the one on top of another. But what you can see is here that there is some sort of crossing. So it's hard to see that there is envelope here. It's like closes, it goes like here. Yes. It just switches too rapidly to see, but goes and here there is something else. So here there is some sort of a bit structure at the end, because you actually map yourself into two eigenstates of the usual Ising model, so with the main walls, and then you get oscillation with this energy gap between the states of the main walls. So this is the SRE, of course, of half of the system. So I cut half of the system, I calculate the symmetry of the entanglements, I plot it even and odd here, and then I have the step numbers here. So after every step, I apply this little bit of scale, with this little bit different parameters, and we see very clearly this rapid oscillation. So there is a nicer graph after all. Let me go talk about the phase transition. So here we studied actually the phase transition with this critical step. So here, this is a critical step. You can find it with the computer. You can, when the envelope crosses itself, and you can see that it actually merges very nicely to half. Yes. So this phase transition actually you have n step divided by half. And now this is a result simulation with a more clear lines. So it is still hard, but there are rapid oscillations here. And here you see that it crosses itself, the envelope crosses itself, because the even and odd now are the same. Yes, because there was some leakage to the other state. and then you have some sort of noise. This is not actually noise if you analyze it very well. And this is what happens, and this is how we detect this Floquet SPT phase condition. So we see it's 125, of course, because we divided it to 250 steps. And this is, as you see, you can actually look about the theta, the angle. So just an angle pi over 4. Here you get the exact phase condition. This is we validated it very clearly in simulation. And we also try to do it on a real quantum computer. So this is on IonQ. And so yeah, it is harder to see here phase condition. You have only 10 steps, but still we see that the experiment can actually figure this out. So you see that the envelope closes very, so you know that there is only 10 steps, but around 7, which is so why it's not 5? Of course, we have just a very small system here, like 5 spins, 10 spins. So it is not really in the adiabatic limit, so it's not close to half of the system. So you see here also, if you just take 100 steps or things like that, you get some deviation. So this is deviation that we understand, but because it matches the simulation very nicely, this is because this experiment doesn't really need this coherence of the points. So they can be lower a little bit, but they need to cross at the exact points. And this is what we see here. So this is very nice. I want to add also, so how much time do we have?
5 to 10 minutes.
So 5,
10.
Okay, so I finish in 5 minutes. So there is an MVQC teleportation protocol that you can actually do with this Floquet operator. So the idea is that we saw that the Floquet operator on the symmetry has some sort of projected representation. But this is the way to think about this. And if we will now some sort of mix the Floquet operator with the symmetry, we may be able to get interesting things similarly to like 1D SPTs when you get this VG projected representation to act with itself in some restricted gates. And so first we start with the symmetric state. So here we have the X symmetry. So all the states are plus. This is the symmetric state. Now we will encode a qubit, just 1 qubit on takes exactly 1 qubit, but it was already discussed that we may have an L length here at the edge of FL and FR. So this is so here is why you need to adiabatically go to a point where you know exactly some of the properties, or you know this is exactly 1, 2, 3 qubits. And so this is why it is hard to generalize it for more than Z2 and so on, but we still can do this. So we will apply some sort of projection. It is also hard. So we want to combine this identity with F, and we need some phase here. So the phase here, just because of the if, the minus I F, always some happen here, but it will give something. So we need to eliminate it somehow. And then you measure the left qubits after you apply this scale, which I'll show in the next slide how to do this. And what you will see that if you measure plus here, you will get your state at the right edge. Now, if you of course measure the minus, you get something with some gate application, so some slight rotation maybe. But we actually see here, so we assume that we got a plus. And now this is the circuit that you actually need to perform. So there you encode your initial state. You do some sort of, this is some standard quantum protocols. So you get phase interference here to somehow kill the different parts that are not with this I plus e to the something else. And if you measure now the left edge, which is this qubit, you will get that your qubit teleported there. So we couldn't actually do it on the real quantum computer because control F is not really available to us. Hopefully, at some point it will be possible. But as you see, this is why this is very complicated. Because control F is not very easy case to implement. But this should work in theory. Okay, so let me add something. So I explained to you why we have degenerate sectors in the SPT, and then I told you how this F operator somehow cycles between the symmetry sectors from plus to minus to plus. But then you can ask me, what about if they are all degenerate? So what do you see? Right? So if I have an SPT phase, like the cluster state, they will all be degenerate, so I will see nothing. So we actually characterize what you can see with this method. So you cannot see everything with this charge pumping, because sometimes we have degeneracies, but you can actually map some sort of, so I call this families. So for example, for Zn, Zn, you will have blocks that are degenerate. So let's say, so I give the example of Z4 times Z4 with the second SPT phase, then you will have 4 blocks that are all degenerate, more 4 blocks that are all degenerate, more 4 blocks. So these blocks, I call them sort of families, yes. And what happens when you apply this charge pumping of the Floquet? It will add you a charge to each of the sectors. So for example, if the charge for Z2 is 0, 1, so it will add 0, 1 to all the sectors. It will cause a cycling, but you will not always see it because some of them will degenerate. So we actually show that for Zn, Zn, you can recognize this GCD of M. Yes, so this is actually what you can recognize from this charge pumping. Because some of them will be degenerates, you will not see them, they will have the same effect. For example, take the cluster state, so it doesn't matter what you add here, either 0, 0, 0, 1, 1, 0, you will always see that all the sectors are degenerate. So you can detect actually nothing. But the GCD will be nothing. Okay, and this is actually what I wanted to say, so let me summarize. So 1D Floquet SPT is the generalized concept from 1D SPT. So we saw how the symmetry resolved entanglement generalizes into some sort of cycling, a very nice the Floquet operator somehow acts with symmetry very nicely. And we saw how the symmetry resolved entanglement actually really characterize many things in these cohomological structures and topological concepts with the symmetry. And the computational power is also, so we can understand it from the algebraic structure. And so, of course, this is just a very simple example of Z2. But we showed, we proved that the MBQC is related to this F and G commutation relations. This is how we prove this. So this is only what we need for our protocol here. This is also the projective representation is of course very related here because you need this maximum non-commutative for cycles, which is related to some sort of factors in this MBQC, which is also in one SPTs. So I want to thank you very much for listening, and if there is time, so I'm not sure if there is time, but
I think we have some time for questions. We started a bit later. So
okay.
What sense? Any questions? Why not asked during the talk?
A question about the Floquet operator. You said, well, we don't care either. I mean, that's just the Floquet operator. You still care that it comes from a Hamiltonian, so it has the local
Yes, yes. So the capitalization can be done with the operator. But you get the component things like the ones that but of course they come from Sonia, but
And so the factorization you have, the FF are minus I F. Can you maybe repeat? You probably said it, but what is that even minus? So FFR live on the edges, and the even minus I with F, that was something that was above, or
okay. So if we think about, let's say, parametric and so this is the H1, H2.
yes,
At a very, very special point. Here. Very diagram. So at this point, for example, well, beta is fine, yes, and alpha can be together. You can see that Z anything will not be cancelled. So you get it to minus pi over 2, and this while they will multiply together, but we get Z1 stuff, and then the L at the right. So let's apply the operators that F and R, and all the other things you can get from H1. Of course, you have this H1 at the start, so you have X1 here, and Xn, you can somehow take them into the set on the left and the right side. You can see that they actually have a very nice commutation activity. So how that complete is X, so it can be commute, minus 1 bar. This is here for this very nice point. But what they hold, okay, is that if you change a little bit this point, and you still have some factor of elements out that have the commutation relation that we want, but you also get this the minus IX generally, and this is where it comes from. So still you see that you have the minus X2, X3, if you do a little bit of the case, you get many different things there. And this is the minus side.
so when you say they, which one of this paper is it?
So don't actually also yes.
Can I have a notion of the string order parameter in a SVP? And if so, how would it sort of differ from the string order parameters in a regular?
So I don't know about the flexibility. So there's the paper. What is the problem? So there are some monitor. And I don't really know how they did what they usually in but even if you can check some I don't remember, but I think all the parameters
The question about your simulation. How many entangling gates were in that simulation that you showed?
So you have
Oh, sorry. Yes, on the, I'm irritated by this echo. You did it on the INQ machine. Yeah, you say when you have this reversal at after 7 time steps. Can you tell us how many entangling gates were involved in that simulation or that?
There were 10 steps, and I think there were 14. So we should have here any probably. So I don't remember exactly how many, but it's that okay if you want a control X and overnight you know left like this and so you get still probably 20 something like that. Maybe even more. And so this taking the estimation, but I have to check exactly how many.
Okay, so it was 5 qubits, 10 cycles, and it's that circuit.
And so here and right, so here I don't there are 10 steps. So I don't remember how many and how many qubits I can check. Okay, and okay. So here, okay, 4 qubits, and the more results here that you can want to see. So we chose this one, right? We want to go something for 4 instead. So here you have 4 qubits, yes.
Okay, thank you.
Not the both from the
And did you say for each subset term you're using 2 CX games?
so that then you can do it by simply have a control X and some additional notation. If you do it correctly, get it in control X and then you rotate somewhere.
Only one per term.
And so yes, one control. No. You don't see what is in the chat.
Also, kind of extending on, did you apply any error mitigation on the INC results? Or it
So no.
just raw results?
So that's how, yeah. Without mitigation, without mitigation, or we can say even a little bit more. Yeah, because you can, especially without the all. In problem. When you measure focus, it's not too much, but when you have more qubits, symmetry is very important here. You don't want to be 0 going into 1, right? That and it's right. We didn't do any mitigation.
So, sorry for this question again, but because it's so important to not exactly this like symmetry or non-symmetry, so your results seem to be quite nice experimental ones. So, but there's like kind of measurement that would expect that if you have like a small number, it would be a big source of error, right? So we all.
Yeah. So if you measure many times, take 10,000 shots. So that's later of them are more terrible. I think the 2 qubits actually. So you can even sustain like 4% without the awaiting and more. And you just lose a little bit of the coherence. So it's here. Right, yeah. You just lose a little bit. Not entirely in the even sector of you like measure so very low thing, but it's a little bit there. And yes, the error appears to come from various sources. And here again, because it's only for things and it's just then it's still not too complicated. So these things around quantum computers and they are getting better. Ion trapping quantum computers is lower with error gate and lower error in general current. So if you do it with ion trapping devices, then you will get nicer results. So you can still see something. Sometimes indeed, even for when you will apply so many games, you use any relation to the field. But in the it works very nice.
Yes, it was all for the questions.